بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. In this video we will discuss tangent planes and normal lines to surfaces in space. And for that, just let's recall the notion of tangent lines for functions of one variable. So in Math 101, if we have a function y equals f of x and a point x equals x0, so this is a curve y equals f of x, and the tangent, we draw the tangent at x0. If we assume that the function is differentiable at x0, i.e. f prime x0 exists, then the slope of the tangent line will be f prime of x0. For the equation of the tangent line will be given in the following by the following equation. It will be y minus f of x0 equals f prime of x0, the slope, times x minus x0. So the situation for functions of one variable is very simple. When we go to surfaces in space, we ask about the tangent plane. So if you have a surface here and I have a point here, I need the tangent plane. Okay. This is the tangent plane at this point. Okay. So now we ask what is really the definition of the tangent plane, and then how to find its equation. We know that a plane, or the equation of any plane, is determined by two things. We need a point in the plane, and we need the normal to the plane. For a given surface at a certain point, the tangent plane is defined as follows. The tangent plane to the surface at this point is the plane passing through the point and whose normal vector, the vector perpendicular to the plane, is the gradient of the surface at that point. The gradient of the surface at that point. So really the tangent plane will be determined by the point and the normal. The normal is just the gradient vector at that point. This is the definition. Once we know the point and we know the normal vector to the plane, we can find easily the equation of the tangent plane. So we have the following here. If we have, let f of x, y, z be a differentiable function of three variables, and let b0, x0, y0, z0 be a point on the surface of x, y, z equals 0. So we have a surface whose equation is of x, y, z equal to 0. We have a point b0 in the surface, and we assume that the gradient of f at the point x0, y0 not equal the 0 vector. At this point, we need the equation of the tangent plane. So this is the tangent plane. By definition, it is the plane whose normal vector, the vector perpendicular to the plane, is the normal vector is given by the gradient. So the normal vector to the tangent plane is the gradient of f at the point x0, y0, z0, which is f sub x, f sub y, f sub z at the point b0. Now, if we know one point and we know the normal vector, then the equation of the tangent plane is very easy to find. Equation of the tangent plane at b0 is given f sub x at the point b0 times x minus x0 plus f sub y at b0, y minus y0 plus f sub z at b0 times z minus z0. So this is equal to 0. So this is the equation of the tangent plane. Related to the tangent plane, we consider also the line perpendicular to the tangent plane. The line perpendicular to the tangent plane. This line is called the normal line. It is a line in space passing through B0 and perpendicular to the tangent plane. This is called the normal line. How to find the parametric equations of this normal line? Well, again, to find parametric equations for the normal, for any line, you need a point, and we have the point, and we need a parallel vector. Here in this case, the parallel vector is really n itself, the normal to the plane, which is the gradient also, which is the gradient of f at x0, y0, z0. Okay. So this is the parallel vector to the normal line. Now, how to find the parametric equations for this normal line? Now, parametric equations of the normal line at the point x0, y0, z0, we use, they are given as follows. So x equals x0 plus f sub x at 0t, and y equals y0 plus f sub y at b0t, z equals 0 plus f sub z at b0 times t, where t goes to minus infinity, from minus infinity to infinity. So these are the parametric equations for the normal line. So really, to summarize, to find the equation of the tangent plane at a point, I need the normal vector, which is the gradient of the surface at that point. With this gradient, I can find the equation of the tangent plane and the parametric equations for the normal line. So now let's illustrate what we did with one example here. Example: find an equation for the tangent plane and the parametric equations for the normal line to the sphere x squared plus y squared plus z squared equals 9 at the point 1, 1, root 7. So we have a sphere and we have a point, and we need the equation of the tangent plane. Again, we need really the normal to the plane, which is the gradient. So the gradient of the sphere. So here I just construct the function here. So let capital F of x, y, z equals the equation of the sphere x squared plus y squared plus z squared minus 9. So let's take this capital F to be this. Now the normal vector, I need the gradient. Okay. So here, what is the gradient of f? Gradient of f x, y, z equals the vector f sub x, f sub y, f sub z. And this equals, when we differentiate with respect to x, we get 2x. With respect to y, and with respect to z, to z. So this is the gradient vector. Now the normal vector to the plane n is just the gradient of f at the given point 1, 1, root 7. 1, 1, root 7. When we substitute, we get 2 times 1, which is 2. 2 times 1, again 2, and 2 root 7. So this is the normal vector to the tangent plane. So this is the normal. This is n, and it is just the gradient of f at the point B. Now, equation of the tangent plane. A plane as normal and a point. Apply the general form of the equation of a tangent plane. It is f sub x 2 times x minus 1 plus f sub y 2 times y minus 1 plus f sub z, which is 2 root 7 times z minus root 7 equal to 0. A point and the gradient, and we can find and the normal vector, and then we can find the equation of the tangent plane. If we simplify, you get 2x plus 2y plus 2 root 7 z equals, this is minus 2, this is minus 4, you take it there, it becomes 4, minus 2 times 7, minus 14, take it there, plus 14, and this is just 18. So this is the equation of the tangent plane. For the parametric equations of the normal line, the same thing. I have a point, and now I need the parallel vector to the normal line. The parallel vector is itself the gradient n. So again, this n, the gradient, forms two things: normal to the plane and parallel vector to the normal line. So now parametric equations for the normal line are the following: x, y, z. Now for x0 it is 1 root 7 plus the vector, the parallel vector. The components are 2 root 7, and then you have t and tn minus infinity to n infinity. So these are the parametric equations for the normal line to the given sphere. Now in the previous part we considered equation of tangent planes to general surfaces in space. Now we'll consider a special case of surfaces. We'll consider surfaces given by functions of two variables. In other words, now the equation of the surface is given by the equation z equals f of xy. Z, a function of two variables. So this is a special case of the general surfaces. If the equation of the surface is given by z equals f of xy, how to find the equation of the tangent plane? This is the special case we'll consider now. So now a special case: find the equation of the tangent plane to the surface z equals f of xy. So the surface is given or expressed as a function of two variables at the point x0, y0. So you have a surface, you have x0, y0, the corresponding image b0, which is x0, y0, z0, and z0 equals of x0, y0. This is the surface, and there is a tangent plane. We need the equation of the tangent plane. The answer here is given as follows. It is the equation of the tangent plane is given by z equals of x0, y0 plus f sub x times x minus x0 plus f sub y times y minus yz. This is the answer. Why did we get the answer? Why we get this answer? Proof here. Really, this is a special case of the previous case. In the previous case, we have an equation. The surface is given as an equation in three variables. So here I can just put z equals f of xy. I can write this as f of xy minus z equals to 0. So I will take this to be my capital f of x, y, z. Okay, f of x, y, minus z. So now the surface, this surface is just capital F equal to 0. Capital F equal to 0. So here this surface now I can write it as capital F equal to 0. Where capital F is just f of xy minus z. With this equation, now I am in the previous situation. So this is the equation of the surface. This is the tangent plane. What is to find the equation of the tangent plane? I need the normal. What is the normal in this case? The normal will be the normal to the plane will be the gradient of capital F. At the point, of course, x0, y0, z0, which is the f sub x, f sub y, f sub z. At the point b0, which is x0, y0, z, z0. Now compute f sub x. F sub x is just little f sub x at x0, y0. Capital F sub y is just f sub y, little f sub y at x0, y0. and f sub z is just minus 1, minus 1. So this is the normal vector to the plane. Now with this normal vector and with the point here x0, y0, z0, we get the equation here. So it is f sub x at x0, y0, x minus x0 plus f sub y x0, y0 times y minus y0 plus, now here minus 1, so this becomes just minus 1 times z minus z0 equal to 0. This is the equation of the tangent plane applying the previous case. Now solve for z, take this to the other side, so this implies the following here. Z equals z0 plus of x, f sub x at x0, y0, x minus x0 plus f sub y at x0, y0 times y minus y0. But what is z0? It is just of x0, y0. So this implies the following. Z equals of x0, y0 plus f sub x at x0, y0 times x minus x0 plus f sub y at x0, y0 times y minus y0. And this is really what is given as the answer here. So this is the form of the equation of the tangent plane in case the surface is given as a function of two variables. One note here, just notice the similarity of the form of the equation in this case to the form of the equation of a tangent line to a curve in Math 101. That is really z, the value of the function, the derivative with respect to x, x minus x0. In Math 101 you have up to here, but instead of f sub x you have f prime at x0. The first part is really similar to the equation of a tangent line in Math 101. Here we add the derivative with respect to y times y minus y0. Now let's illustrate this special case with one example. Example, find the equation of the tangent plane to the paraboloid z equals x squared plus y squared at the point 1 and 1. So you have a paraboloid here, and here in the xy plane I have 1 and 1, and this is the corresponding point on the paraboloid. Solution, the solution here, well, the equation here we have of xy, of x y, just x squared plus y squared. This is the equation itself, the function of two variables. Now, the equation of the tangent plane is given as follows. This is z equals of f, the value of the function at the point 1 and 1, plus f sub x at 1, 1 times x minus x0, which is 1, plus f sub y at 1, 1 times y minus y0, which is again 1, which is 1. Now we have just to substitute. So here f sub 1, 1 of 1, 1, it is 1 plus 1, which is 2, 1 squared plus 1 squared equals 2. F sub x, first I need to find f sub x at xy, which is just 2x. So this implies f sub x at 1 and 1, this is also 2, and f sub y of xy equals 2y, and hence f sub y at 1, 1 equals 2. Now substituting the equation, I get the following here. Z equals 2 plus f sub x is 2 times x minus 1 plus f sub y again 2 times y minus 1. If we simplify, we get the following. So this is z equals 2x plus 2y, 2 minus 2 minus 2, this becomes minus 2. So this is the equation of the tangent plane to the given paraboloid at the given point. Let's consider now the following problem. Find the equation of the tangent plane and the parametric equations for the normal line to the surface x squared y plus z squared equal 10z at the point b minus 3, 1 and 1. So we need equation of a tangent plane, and for a tangent plane you need a point, and the point is given, and we need the normal line. What is the normal line in this case? The normal line is just the gradient of this surface. So what is the equation of this surface? We just take this term to the other side. So here x squared, the surface x squared y plus z squared minus 10z equal to 0. So I take this to be my capital of x, y and z. This is x squared y plus z squared minus 10z. So the equation of the surface is just f equal to 0. This is the equation of the surface. Now the normal is the gradient of the surface of this equation. So now find the gradient of f at x, y, z, and it is f sub x, f sub y, f sub z. And compute f sub x is just 2xy, and f sub y is just x squared, and f sub z, it is 2z minus 10. So this is the gradient vector as a function. Now the normal vector to the tangent plane is just the gradient at the given point, minus 3, 1, 1, minus 3, 1 and 1. And this equals the following vector. 2 times minus 3, minus 6, and this is 9, and 2 minus 10, minus 8. So this vector here, is the normal vector to the tangent plane. So what is the equation of the tangent plane? Equation of the tangent plane is given by the following equation. I have minus 6 times x minus 3 plus 9 times y minus y0, which is 1, plus minus 8 times z minus z0, which is 1, equal to 0. Simplify, just multiply. This is minus 6x minus 18 plus 9y minus 9 minus 8z plus 8 equal to 0. And this is just minus 6x plus 9y minus 8z. Here minus 18 minus 9 minus 27 plus 8 minus 19. You take it to the other side, becomes 19. So this is the equation of the tangent plane. For the parametric equations of the normal line, well, for the normal line I need a point, it is given, and a parallel vector. The parallel vector in this case is again n, the same as the normal vector. So this is also the parallel vector to the normal line. So the parametric equations of the normal line are given by the following. So this is x, y, and z. I have the point minus 3, 1, 1. So this is minus 3, 1, 1, plus the components of the parallel vector, which is minus 6z minus 6t plus 9t plus minus 8t. where Tn minus infinity to n infinity. So these are the parametric equations for the normal line. That's it. Now we consider the following problem. Find the equation of the tangent plane to the surface z equals x e minus y plus 1 at the point 2, 0. Here the equation of the surface is given as a function of two variables. Z equals a function of two variables. So here really f of xy equals x e power minus y plus 1. And the surface is given as z equals f of x, y. In this case, the equation of the tangent plane has a nice form, which is similar to the equation of the tangent line in Math 101. So here the equation of the tangent plane is given as follows. Okay. Z equals of f at the point 2, 0 plus f sub x at the point 2, 0 times x minus 2 plus f sub y at the point 2, 0 times y minus 0. So this is the form of the equation in this case. We need just to compute f and f sub x and f sub y at the point 2, 0. So here f of 2, f at 2, 0, when we substitute you get just 2 e power 0 plus 1, which is just 3. Now f sub x at xy, f sub x, it is just e power minus y, So this implies f sub x at 2, 0. This is just e power 0, which is 1. And f sub y at xy equals x e power minus y times minus 1. Now at the point 2, 1, at the point 2, 0, f sub y at 2, 0. When we substitute, we get just minus 2. Now substitute these values in the equation. So this implies the following. Z equals 3 plus f sub x, which is 1, times x minus 2 plus f sub y, which is minus 2, times y minus 0, which is just y, or y minus 0. Let's simplify. So this becomes z equals 3 plus x minus 2 minus 2y, and hence z equals x minus 2y plus 1. So this is the equation of the tangent plane to this problem. Now let's consider the following problem. Find the points e0, x0, y0, z0 in the surface x squared plus 4y squared minus z squared equals 9, where the tangent plane is parallel to the plane 2x plus 2y plus z equals 1. So we have a surface and we have a tangent plane. This tangent plane is parallel to another tangent plane. We need to find the points on that surface where the tangent plane to the surface is parallel to the other, or to the given plane. Of course, when you have two tangent planes, we have to find a relation between them. If two planes are tangent, then the normal vectors to both are parallel. But this is the first observation. Tangent plane 1. So if you have a plane 1 parallel to plane 2, this implies the normal to the first one, n1, is parallel to the normal to the second vector. From the given information that the two planes are parallel, we conclude that the normal vectors to both of them are parallel also. So here I have to find n1 and n2. what is my P1 and what is my P2? So I will take just here P1, tangent to the surface, tangent to the surface at B0, X0, Y0, Z0. So this surface. Well, how to find N1 at this point? For this surface, the normal to the tangent is the gradient at the point. So here N1, just the gradient of F at the point X0, Y0, Z0, where my F will be the whole equation, capital F of X, Y, Z equals X squared plus 4Y squared minus Z squared minus. This is my capital of capital F. Now find the gradient. So this is the gradient now. F sub X, F sub Y, F sub Z. F sub X, F sub Y, F sub Z at the point B0. So this is just 2x. This is 8y. And this is minus 2z at the point B0, which is just 2x0, 8y0, minus 2z0. So this is the normal vector to the first plane, to the tangent plane, What about the normal into of the given plane? So the given plane now here, B2, it is the given plane, 2x plus 2y plus z equals 1. Now into the vector normal to the second plane, we can read it from the coefficient 2, 2, and 1, 2, 2, and 1. So this is N2. Now the two planes are parallel. Then what is the relation between the two normal vectors? They are also parallel. So now, but if the two vectors N1 is parallel to the second vector N2, this implies the following. Two vectors are parallel if and only if they are multiples of each other. So this means N1 equals K N2 for some constant, K. They are multiples of each other. Now substitute. So here you have the following. N1, which is 2x0, 8y0, minus 2z0 equals K times N2, which is 2, 2, 1. 2, 2, and 1. And this is just, if you multiply K by the vector by K, this gives us 2K, 2K, and K. A vector equals another vector. We have equality of vectors. Two vectors are equal if the corresponding components are equal. So just equate the corresponding components. So this is 2x0 equals 2k, 8y0 equals 2k, and minus 2z0 equals k. Then what is x0? What is y0? What is solve for x0? So this is x0 equals k, y0 equals 1 over 4 k, and z0 equals minus half k. So we find the points x0, y0, z0 in terms of k, a variable, a constant, some k. To find the point then, x0, y0, z0, we have to find the value of k. Well, how to find the value of k? Well, we know that the point x0, y0, z0 lies on the surface. then this point satisfies the equation of this surface. So substitute this point in the equation of the surface. Substitute in the equation of the surface. So I have x0 squared, k squared, plus 4y squared, so this is 4, and this is 1 over 4k squared, minus z minus half k squared equals 9. And simplify, this is just k squared plus 1 over 4 k squared plus or minus 1 over 4 k squared equals 9. So the last two terms here cancel. So you get k squared equals 9, and hence k equals plus or minus 3. Plus or minus 3. So I have two values of k. Substitute these values of k in the equations here to get x0, y0, z0. So here if k equals 3, I get the following: x0, y0, z0. Substitute k equals 3, so this is 3, 4 over 3, 3 over 4, and minus 3 over. So this is the first point. When k equals minus 3, again substitute, you get x0, y0, and z0. When k equals minus 3, I get minus 3 here, and here minus 3 over 4, and 3 over 2. So in fact we have 2 points on the surface at which the tangent plane is parallel to the given plane. So these are the 2 points. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we'll talk about linearization for functions of 2 variables. And to understand this concept for functions of 2 variables, it is advisable to just recall this concept for functions of 1 variables. Linearization for functions of 1 variable. Because really the situation is just a generalization to functions of 2 variables. So for that, let's recall the notion of linearization for functions of 1 variable. So in Math 101, we have let y equals f of x be a differentiable function at x0. And naturally, the question is to find the slope of the tangent line to the curve at the point x0. And the slope is f prime x0, and then the equation of the tangent line at x0 is given by y equals f of x0 plus f prime x0 times x minus x0. So this is the equation of the tangent line to the curve at x equals x0. Now we take the equation of the tangent line and we give it a special name. We call it the linearization of f at x0. So here we have the following definition. The linearization of f at x0 is just denoted by L of x, and it is equal only just the equation of the tangent line. So it is L of x, it is f of x0 plus f prime at x0 times x minus x0. So this is the definition of linearization for functions of 1 variable at a point. It is basically the equation of the tangent line. From this linearization, we get an approximation for f. We get the linear approximation of f at x0. So here, usually we approximate the curve by the tangent line when we are around x0. The function is approximated by the tangent line, or now by the linearization. So we have the following linear approximation. So we have the function of x is approximately equals the linearization L of x, where near x0, when x is near x0, when we are very close to the point x0 around x0. So the approximation is valid when we are around x0. So this is the definition and the application or the importance of the linearization. We can use the linearization to approximate the function around a point. This is for functions of one variable. For functions of two variables, the situation is exactly the same. It is just a mere generalization. We have a surface, we have a tangent plane. We use the tangent plane to approximate the function. And we call the equation of the tangent plane linearization. Linearization of the function of two variables. So it is really the situation for functions of two variables is just a mere generalization for the concept of in functions or the functions of one variable. So now let's take z. Let z equals f of xy be a differentiable function at a point x0, y0. We have the graph, the surface of the function, and at point x0, y0 we have a tangent plane. The equation of the tangent plane at x0, y0 is given by this equation. Now we define the linearization of f at x0, y0 to be just the equation of the tangent plane. The notation, the linearization of f of xy at x0, y0, the notation is L of xy, and it is just the equation of the tangent plane. This is f of x0, y0 plus f sub x at x0, y0 times x minus x0 plus f sub y at x0, y0 times y minus y0. So this is the definition of the linearization for a function of two variables. In a similar manner that we use for functions of one variable, we use the linearization as an approximation to the surface or to the function. So the linear approximation of f at x0, y0, so here around x0, y0, around in a small neighborhood about x0, y0. The linear approximation is the following: f of xy, we approximate it by L of xy. When xy is near the point x0, y0. And when we say near, it is very close or around the point x0, y0. So this is really the definition of linearization and the linear approximation for a function of two variables. As we said, it is just a mere generalization to the situation for functions of one variable. You have a curve, you have a tangent line. Well, the linearization is just the equation of the tangent line. We approximate f by the tangent line. Here we have a surface and we have a tangent plane. The tangent plane is called the linearization. We use the linearization, tangent plane, as an approximation for the value of the function around x0, y0. So this is the definition of linearization and linear approximation. Now let's illustrate what we explained by an example. Let f of xy equals square root of xy and be the point 1 and 1. Find the linearization of f of xy at the point b, 1 and 1. Part b, approximate the value of 1.01, 0.9. So we need to find the linearization first. We apply the definition. So the linearization of this function is the following: L of xy equals of f of the point is 1 and 1, f of 1, 1 plus f sub x at 1, 1 times x minus 1 plus f sub y at 1, 1 times y minus 1. This is the formula for the linearization. It is just the equation of the tangent plane. Now we compute f sub 1, 1 and f sub x and f sub y at 1, 1. So first, f of 1, 1, it is just square root of 1 times 1, which is just 1. F sub x at xy, the derivative, with the partial derivative with respect to x, it is just 1 over 2 root x y times y. So this implies f sub x at 1, 1. When we substitute, we get half. F sub y at xy, it is also 1 over 2 root xy times x. Now, when you substitute at 1 and 1, of sub y at 1, 1, this is again half. So now substitute. So this implies L of xy equals 1 plus half times x minus 1 plus half times y minus 1. So this is the linearization of f at 1 and 1. We can leave it like this, or we can simplify. So this just multiply. This is half x plus half y. Well, minus half, which is minus 1 plus 1, 0. So this is the linearization. For part B, approximate the value of the function at the point 1, 0.01, comma 0.9. For approximation, we use the application of the linearization. So here, the main application of linearization is the following. So we have f of x, y, is approximately equals the linearization when xy is near the point 1 and 1. This is the main application of the linearization. We use linearization to approximate the values of the function around a specific point. Now here, from the previous part, this implies f of xy is approximately equals half x, this is half x, plus half y. This is the L of xy when xy is near 1 and 1. Now I need to find the value of the function at the point 1.01 and 0.9. Now this point is close to 1 and 1. So I can apply this approximation. Since the point 1.01 comma 0.9 is close or near the point 1 and 1, then I can apply this approximation. Here f of 1.01 comma 0.9 approximately equals half times 1.01 plus half times 0.9. And this implies f of 1.01, 0.9 is approximately equals, this is to 1.91, and this is just 0.9555. So this is the approximate value of the function at the point 1.01, 0.9. Let's consider the following problem. Find the linear approximation of f of xy equal len 3x minus y at the point 1 and 2. To find the linear approximation, first we have to find the linearization. So the linearization is L of xy. By definition, this is f of at the point 1, 2, f of 1, 2 plus f sub x at 1, 2 times x minus 1 plus f sub y at 1, 2 times y minus 2. This is the definition of the linearization. Now evaluate f and f sub x and f sub y at the point 1 and 2. So here I have f of 1, 2, f of 1, 2. This is f of len. When you substitute, you get 3 minus 2, and this is len 1, which is 0. F sub x f sub x at xy. We find the derivative with respect to x. This is 1 over 3x, 1 over 3x minus y times 3 by the chain rule, times 3. So this implies f sub x at 1 and 2 equals, I have a 3 here, at 1 and 2, 3 minus 2, 1, so this is just 3 over 1, and this is a 3 also. F sub y at xy equals 1 over 3x minus y times minus 1, derivative of minus y. When we evaluate at 1, 2, f sub y at 1 and 2, this is minus 1 over 1, and this is just minus 1. Now substitute these values in the linearization. So this is L of xy equals 0 plus f sub x is just 3 times x minus 1 plus f sub y, which is minus 1 times y minus 2. If we simplify, this is just 3x minus 3 minus y plus 2, and hence this is 3x minus y minus 1. This is the linearization. Now what is the linear approximation? Then the linear approximation is the following: of xy is approximately equals L of xy. Of course, so this approximation is valid when xy is near the point 1 and 2. Again, around the point 1 and 2. So this implies f of xy is approximately equals the equation of Lxy. This is 3x minus y minus 1 when xy is near the point 1 and 2. So the linear approximation of the function, which is len 3x minus y, it is approximately equals this linear equation, 3x minus y minus 1. But again, the approximation is valid around the point 1 and 2. Let's consider the following problem. Let f of xy equals x over x plus y and b be the point 1 and 0. A. Find the linearization of f of xy at the point 1, 0. B. Approximate the value of f of 0.9, comma 0.1. For part A, to find the linearization, we apply the formula for the linearization. So this is the formula: L of xy equals f at the given point 1, 0, f1, 0, plus f sub x at 1, 0 times x minus 1, plus f sub y at 1 and 0 times y minus 0. This is the formula for the linearization. Now we have to compute the value of f sub x and f sub y at the point 1 and 0. So of 1, 0, when we substitute, you get 1 over 1 plus 0, it is just 1. F sub x, first we find the partial derivative of f with respect to x. Apply the quotient rule. This is x plus y, x plus y squared, the denominator x plus y times 1 minus x times 1. And when we simplify, we get the following: x plus y squared. This is x minus x plus just y. So this implies f sub x at 1 and 0. F sub x at 1 and 0. This is just 0 over 1 plus 0 squared, and this is just 0. This is f sub x. F sub y, this is f sub y at x, y. Again, just apply the quotient rule, x plus y. The denominator, x plus y, time derivative of the numerator with respect to y, this is just 0, minus y, time minus x, time derivative of the denominator with respect to y, which is 1. So this gives us just minus x over x plus y all squared. We evaluate this at the point 1, 0. This implies f sub y at 1, 0. This is just minus 1 over 1 plus 0 all squared, and this is just minus 1. Now we take these three values and substitute. So this implies L of xy equals, this is off of 1, 0, it is just 1, plus f sub x is 0 times x minus 1, plus f sub y, which is minus 1, times y minus 0. When we simplify, this is just 1 minus y. So this is the linearization of f at the point 1 and 0. Now for part B, approximate the value of the function at point 9.1. Well, this is now we apply the application of linearization. We use linearization to approximate the function. So for part B, we have the linear approximation. The linear approximation is the following: f of xy approximately equals L of xy when xy is near the point 1 and 0. So we have this linear approximation. Now this gives us the following: this gives us f of xy is approximately equals L of xy was found to be 1 minus y, again when xy is near the point 1 and 0. Now with a given point, since the point 0.9, point 0.9 and 0.1 is really close to the point 1 and 0. Since it is close to it, then we can apply this approximation. Is near or close is near the point 1 and 0, then we can apply this approximation of 0.9, point 1 is approximately equals 1 minus y. Y is just 0.1. So this gives us the following: the value of the function of 0.9, point 1 is approximately equals 0.9. So this is the approximation. Let's consider the following problem. Let f of xy equals x times e power xy. Use a suitable linear approximation to approximate the value of f at the point 0.001 minus 0.002. So to solve this problem, we have to find a linear approximation for f. Well, the linear approximation for f is given by following. Generally, the f of xy is approximately equals L of xy. So it equals its linearization. But here we have to make the approximation near a point. When xy is near some point. Now this point is not given in the problem. Use a suitable linear approximation to approximate this value. Well, we use the reverse way. We look at the problem in a reverse way. We have to find the point. We have to find a suitable point. How to choose a suitable point? Well, choose a simple point near the given point here. The natural choice for our main point is just 0 and 0. Notice this point is very close to the origin. So we can find the linear approximation when xy is near the point 0 and 0. Why? Because really the given point where we need to find the approximation is close to the origin. So choose 0, 0. Find the linear approximation at 0, 0. For that, we have first to find the linearization L of xy at 0, 0. This is by definition of 0, 0 plus f sub x at 0, 0 times x minus 0 plus f sub y at 0, 0 times y minus 0. Okay. We now find the value of the function f and f sub x and f sub y at 0, 0. And we observe the following of 0, 0. When we substitute, we get 0. We need to find f sub x at xy. So we differentiate with respect to x. We apply the product rule. So it is the first x times derivative of the second e power xy times y plus the second e power xy times derivative of the first, which is 1. So this equals e power xy times xy plus 1, xy plus 1. Evaluate at 0, 0. So this implies f sub x at 0, 0. This is e power 0, 1. 0 plus 1, you get 1. The same thing for f sub y at xy. When we differentiate with respect to y, x is constant, so this is just x times e power xy times x. And this is just x squared e power xy. When you substitute f sub y at 0, 0, you get just 0. Substituting L, so this gives us the linearization L of xy equals 0 plus f sub x is 1 times x minus 0 plus f sub y is 0 times y minus 0. And this is just x. This is just x. So this is the linearization. From the linearization, we get the linear approximation. So now, this gives us f of xy is approximately equals L of xy, which is just x, when xy is near the origin. Now we can evaluate or we can estimate the value of this function because this point is now very close to the origin, so we can apply the given approximation. So here, since the point 0.001 minus 0.002 is near the origin 0, 0, then we can apply this approximation. So here, this is just off of 0.001 comma minus 0.002 is approximately equals just x minus 0.001. So this is the approximated value for the function at 0.001 minus 0.002. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we'll discuss the notion of differentiability for functions of two variables. Okay. And for that, we start with functions of one variable, and just let's recall the definition of differentiability for functions of one variable. When we have a function of one variable y equals f of x, then the definition f is differentiable at x0, at a point x0, if f prime x0 exists. Basically, a function is differentiable at a point if we can differentiate it, if we can find the value of the derivative at x0. Geometrically, this means we can draw a tangent line. We can draw a tangent line to the curve at x0, as indicated in this graph. So this is the definition of differentiability for functions of one variables. For functions of two variables, the situation is a little bit more complicated So let's see what is the definition for the differentiability for functions of two variables. So let's take a function of two variables, z equals f of x, y. First, we have the first definition. If a point moves from x0, y0 to x0 plus delta x, y0 plus delta y, so from one point to another point with change in x equal delta x and change in y delta y, then the corresponding change in z along the range is given by delta z, f at the terminal point minus f at the initial point. So this is the change in z when we move from the point x0, y0 to x0 delta plus delta x, y0 plus delta y. Now for differentiability, the definition, f is said to be differentiable at the point x0, y0 if two conditions are satisfied. First, we have to check that f sub x and f sub y, both of them exist at the point x0, y0. The second condition is delta z, which is the change in z. Delta z has to satisfy the following equation. Delta z equals f sub x at x0, y0 times x minus x0 plus f sub y x0, y0 times y minus y0 plus epsilon 1 delta x plus epsilon 2 delta y. Epsilon 1 and epsilon 2 are functions of x and y, functions of two variables, and we require that epsilon 1 and epsilon 2 approach 0 as delta x and delta y approach 0. So for differentiability, f sub x and f sub y have to exist at the point x0, y0, and delta z has to satisfy this equation. This is the definition of differentiability, and as you can see, it is really more complicated than the definition of differentiability for functions of one variable. To get a feeling of what this definition means, in fact, we can get some feeling of the meaning of differentiability here by combining the two equations, delta z here, the change in z, and delta z in this equation. In fact, if we combine these together, we get the following equation. F of x0 plus delta x, y0 plus delta y equals f of x0, y0 plus f sub x, f sub y plus epsilon 1 plus epsilon 2. This is if we combine them together. Okay. And if we look at this equation, notice this expression here. Okay. These three terms. This by definition is called the linearization of f at the point x0, y0, or the equation of tangent plane, or equation of the tangent plane at x0, y0. So this equation says, well, the value of the function near x0, y0 equals the linearization or the tangent plane plus some quantity, If we just restrict on this, of this part, if we remove the last two terms, then equality will be changed to approximation. So this says really near x0, y0, the function can be approximated by the equation of the tangent plane at x0, y0, which is really similar to what we have in Math 101. Near x0, the function can be approximated by the equation of the tangent line, okay, or by the linearization also. They are the same thing. Okay. So this is a feeling of the meaning of differentiability. In practice, of course, to check differentiability, in practice we do not use this definition here. In practice, we use the following theorem to simplify our check for differentiability. So we have a test for differentiability. So let z equals f of x, y. If we want to see whether a function is differentiable at a point x0, y0, we have to check two conditions. The first condition, we have to check that f sub x and f sub y exist near x0, y0. And we mean by near x0, y0 in a small region containing x0, y0. The second condition, we have to check that f sub x and f sub y are continuous at x0, y0. If these two conditions are satisfied at a point x0, y0, then we say that f is differentiable at that point. So this is a quick and a simple test to check differentiability at a point. Differentiability on a region, if f sub x and f sub y exist and continuous on an open region R, then we say that f is differentiable at every point in R. So this is checking differentiability at a point, and this is checking differentiability on an open region. One last thing here, which is we have a small fact which is similar to functions of one variable. In Math 101, if you have y equals f of x, we know that if the function is differentiable at a point, then it is also continuous at that point. This fact also holds for functions of two variables. And we have the following here. Let z equals f of xy. If f is differentiable at a point x0, y0, then f is also continuous at x0, y0. Let's consider the following problem. Show that the function of xy equals x cubed y minus y squared plus 1 is differentiable at the point 1, 1, 2. To show this, we have to check two conditions. The two conditions are the following. The first condition, just f sub x and f sub y exist near the point 1, 2. So around the point 1, 2, in a region around containing the point 1, 2. And the second condition, f sub x and f sub y are continuous at the point 1, 1, 2. So these are the two conditions that we have to check. And for that, then we have to compute f sub x and f sub y. So what is f sub x here? F sub x at xy, differentiating with respect to x, we get a 3x squared y minus 0 plus 0, and f sub y equals xy equals x cubed minus 2y. So these are f sub x and f sub y. As we notice here, they are really polynomials on two variables. So really here, f sub x and f sub y exist at any point in the plane, in the xy plane. I can substitute any value, any point a, b, and then I will get a real number. Since they exist at any point, then and so they exist near the point 1, 1, 2. Okay. Near the point 1, 2. I can substitute any point near 1, 2. I will get a real number. They are defined. Okay. The second condition also here, both of these f sub x and f sub y, again they are polynomials into variables. They are continuous everywhere. Okay. F sub x and f sub y are continuous at any point in the xy plane, Notice that the domain of the function is all points in the xy plane. Okay. They are continuous at any point, and hence, and so they are continuous at the specific point 1 and 2. 1 and 2. So the two conditions are satisfied. Conclusion, this implies f is differentiable at the point 1, 1, 1. So this is how to check differentiability at a point for this function. Let's consider the following problem. Find all points at which the function of xy equals ln 1 minus x squared is differentiable. The first thing here, we have to find the domain of the function. Just the domain is the set of all points xy, such that the quantity inside the ln y minus x squared has to be greater than 0. And this, we can write it in this manner also. This is just the set of all points xy such that y greater than x squared. If we want to sketch the domain, the domain again in the points in the xy plane, and we have the parabola y equals x squared. So this is y equals x squared. So this is y equals x squared. We need all points where y greater than x squared. So the points will be everything inside the parabola, every point here. So this is the domain of this function. Everything above the every point above the parabola. So now we'll try to find at which points in the domain is the function differentiable. So we'll concentrate only at the points in the domain of x. And to check differentiability at a point or at a region, first at a point, we have to check f sub x and f sub y. So we have to find first f sub x. So this is f x y. When you differentiate it, you get 1 over y minus x squared, and this is minus 2x. And f sub y at xy, this is 1 over y minus x squared, and this is 1. Now we need to know at where do f sub x and f sub y exist, and where do they where are they continuous. And you can see both exist, so we have to check existence and continuity. And we can see easily that really f sub x and f sub y exist at every point and also continuous at every point except where y minus x squared equal to 0. So f sub x and f sub y exist and continuous and are continuous at every point except where y equals x squared, at every point except when y equals x0, i.e. when y minus x squared equal to 0, we get y equal to x squared. This means, but the points where the functions do not exist and are not continuous are the points on the parabola. But the points on the parabola are not in the domain, so they do not concern us. Any points away from the parabola in the domain, both will exist and both are continuous. So in that case, inside the domain, the two conditions are satisfied, existence and continuity, and hence the function is differentiable at every point in the domain. So this implies f sub x, let me see, and f sub y exist and are continuous at every point in the domain of f. The two conditions are satisfied at any point in the domain. So this implies f is differentiable at every point in its domain. At every point in the domain of f. So to summarize, the given function is differentiable on its domain at every point above the parabola. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we will discuss the notion of differentials for functions of two variables. And to make this notion clear and simple, it is better to start recalling the notion of differentials for functions of one variable. In fact, once we recall this, or once we understand this notion for functions of one variable, we will see that the situation is really a mere generalization to functions of two variables, specifically for graphical reasons. If we understand this notion for functions of one variable, and we illustrate this geometrically or graphically, then the situation is similar. And then when it comes to graphing functions for two variables, at least on the board, the graphs might not be as good as we want them. So once we understand this notion for functions of one variable, we will see the generalization is so obvious. So for that reason, let's start recalling the notion of differentials for functions of one variable. So let's take y equals f of x, a differentiable function. By definition, the differential of y is defined as dy equals f prime of x dx. dy is the notation for differential of y, and dx is the notation for the differential of x. Dx and dy, in this definition, we look at this dx, the differential of x, as just an independent variable that can take any real number. And the differential in y dy, we'll look at it as a dependent variable. It is a dependent variable that depends on dx and the x itself, or plus the function. So this is the definition of the differential of y for a function of one variable. To understand the geometric meaning of this, we just make the following. Well, if x changes from x0 to x0 plus delta x, then the corresponding change in y is just the difference, delta y. The change in y, the exact change in y, is f of x0 plus delta x minus f of x0. Again, we recall the linearization of a function at x0. It is just the equation of the tangent line at x0. So it is given by L of x equals f of x0 plus f prime x0 times x minus x0. Now let's illustrate these delta y and Lx graphically. So we have a function y equals f of x. This is the curve. At x0, there is the tangent line, and the equation of the tangent line is just the linearization of the function. Now, if x changes from x0 to x0 plus delta x, then what is the corresponding change on the curve itself? At x0, the function is f of x0. At x0 plus delta x, the value of the function is f of x0 plus delta x. The change in y on the curve will be this distance from here 2 here. So this is delta y. It is the difference of x0 plus delta x minus of x0. So this is the change in y along the curve graphically. Now what we will do here, we will try to find the change in y along the tangent line. What is the change in y along the tangent line? So along the tangent line, the change in L here, in y, which is just L, delta L, it is L of x0 plus delta x minus L of x0. Computing the change, as x changes from x0 to x0 plus delta x, we will compute the change in y along the linearization, or along the tangent line. What is this difference here? Well, we have a formula for L, which is the equation of the tangent line. So we substitute, so this gives us the following. This is f of x0 plus f prime x0 times x, which is x0 plus delta x minus x0. So this is the first term, minus L of x0 minus L of x0. So this is f of x0 plus f prime at x0 times x0 minus x0. So when you substitute x0 here, I get x0 minus x0 here. Let's simplify. Now here, this term will be 0. x0 minus 0 is 0, so this is 0. Of x0 minus of x0. So these two terms again will be cancelled. I will end up with the following: f prime of x0, x0 minus x0 times delta x. Okay, so the change in y along the tangent line is f prime x0 times delta x. Now delta x is the change in x. Well, if I compare the definition, of the differential and the change in y, I will notice here that the only difference is just in dx here and delta x is there. Since dx is independent variable, can take any real value, we usually let dx equal delta x, always, this independent variable. In this case, I have f prime at x0 dx. So what is this? F prime at x0 dx, it is just the differential in y, dy, evaluated at x equals x0. So now, the change in y along the tangent line, we go from this point to this point, along the tangent line, this is f of x0, this is the L of x0 plus delta. This change is dy. At x0, So this is now delta y and dy. So this means with the following. To summarize, when x changes from x0 to x0 plus delta x, there are two changes. One along the curve and one along the tangent line. The change along the curve is delta y. So this is the exact change in y along the curve. The change along the tangent line is dy. The change along the tangent line is dy. Okay, so this is the geometric meaning of the differential. So the differential dy is just the change in y. So still it is a change in y, but not along the curve. It is along the tangent line. So this is the geometric meaning of the differential. One observation from the graph here, notice what happens if delta x is very small. If delta x is very small, i.e. x0 plus delta x, very close to x0. Then compare delta y and dy. Well, the difference between them is this one. This is that at this point, this is the difference between delta y and dy. If delta x is very small, the difference will be get smaller. So this is the next difference. Then this is the next difference, and this is the next difference. As this point goes to x0, the difference between delta y and dy becomes very, very small until it becomes almost equal. Okay. If delta x is very, very, very small. So from this really we get the following. We get the following approximation. If delta x is very small, then when delta x is very small, we have then delta y is approximately equals the dy, i.e. the change along the curve is approximately equals the change in y along the tangent line. So this is the application or the main application of differentials. This is the situation for functions of one variable. For functions of two variables, we will see it is exactly a mere generalization. Now, having reviewed the notion of differentials for functions of one variable, for the functions of two variables, the situation is really similar. So now let's just see what we have. So let z equals f of xy be a differentiable function. By definition, the differential of f or of z, we say, is defined as dz equals f sub x dx plus f sub y dy. We write dz or df, the differential of f or the differential of z. So for functions of one variable, we have only one part, f prime dx. For functions of two variables, you have the two types of derivatives, f sub x and plus f sub y. So this is the definition of the differential of a function of two variables. dx and dy are the differentials in x and the differential in y. We look at them as independent variables, and so they can take any real number. dz, we look at it as a dependent variable. So really it is a variable that depends on dx, dy and the point x and y. So up to now, really, the definition is just a generalization of the differentials of one for functions of one variable. So you have, this is the definition. Now, for a function of two variables, the graph is a surface. A surface. Now, if a point changes from x0, y0 to another point, what is the change in z, or the change on the value of the function on this surface? If xy changes from x0, y0 to x0 plus delta x, y0 plus delta y, then the corresponding change in z on the surface, the corresponding change is just the difference. Delta z equals f of x0 plus delta x, y0 plus delta y, minus f of x0, y0. F of terminal minus f of initial. So this is the change in the value of z, or in the value of the function on the surface. Z equals f of xy. Again, we recall the linearization of a function at x0, y0. The linearization is just the equation of the tangent plane. And the equation of the tangent plane is given as well. So the linearization of f at x0, y0 is L of xy, f of x0, y0 plus f sub x, x0, y0, x minus x0 plus f sub y times y minus y0. The linearization is just the equation of the tangent plane. So you have a surface and you have a tangent plane. We measured the change in z along the surface. Now let's measure the change in z along the tangent plane. So in the tangent plane, if xy changes from x0, y0 to x0 plus delta x, y0 plus delta y, then the corresponding change in z, or in L on the tangent plane, is delta L, L of terminal minus L of initial. Substitute x0 plus delta x, y0 plus delta y in the equation of Lx. When we substitute, we get this quantity. Minus L of x0, y0. When I substitute x0 and y0, these two terms will be 0. I will end up just with f of x0, y0. Well, here the first term with the last term will cancel, so I will end up with these two terms. Now delta x and delta y. For the differentials, again always I will choose dx to be always delta x and dy to be always delta y. So in this case I will get the following: of x, x0, y0, dx plus f sub y at x0, y0, dy. What is this expression here? It is just the differential in z evaluated at x0, y0. So this is just dx, dz at the point x0, y0. So now, what is delta L? What is dz, the differential at a point? It is just the change along the tangent plane. Okay. So we have really a surface, to summarize, a surface and a tangent plane. A point moves from x0, y0 to another point. There is a corresponding change along the surface and a corresponding change along the tangent plane. The corresponding change along the surface is delta z. The corresponding change along the tangent plane is dz. This is the geometric meaning of the differential of z, or a differential of a function of two variables. As in the case for functions of one variable, when delta x and delta y are very small, then we get the approximation. The differential, the exact change delta z, the exact change along the surface is approximately equals the change, the differential dz, which is the change along the tangent plane. The change, delta z is approximately equals dz, which can be read as follows: the exact change on the surface can be approximated by the change on the tangent plane. So this is the situation or the definition of differentials for functions of two variables, and the application. The application is really the differential can be used to approximate the change along the surface itself. And let's consider the following problem. Let z equals x sine y squared. Find the differential of z. To find the differential of z, we have just to apply the definition. So here we have really f of xy equals x equals sine y squared, and the function is the following: z equals f of xy. The definition of the differential of z, well, definition it is dz equals f sub x at xy dx plus f sub y at xy dy. This is the definition. So we need just to compute f sub x and f sub y and then just plug them in. So here, what is f sub x? When you differentiate with respect to x, I get sine y squared, sine of y squared times dx, plus, when we compute f sub y, when we differentiate with respect to y, I get the following: this is x, and this is cosine y squared times 2y. This is f sub y times dy. Well, I can rewrite it as follows: this is sine y squared dx plus 2xy cosine y squared dy. So this is the definition, and this is the differential of z for the given function. Let's consider the following problem. Let z equals x squared minus 2y plus 3. Use differentials to estimate the change in z when xy changes from the point 1, 2 to the point 0.9, 2.1. Solution here. Of course, here this is really the main application of differentials, which is estimating or approximating the exact change. So we need to estimate the change in z, the exact change in z. The exact change in z is just delta z. Well, we can approximate this by differentials, dz. When xy changes from 1, 2 to 0.9 and 2.1. So the change in z, the exact, is approximately equal dz, but dz evaluated at the point 1 and 2, So this is the main formula. For this, I need just to compute dz. So what is dz? dz, the differential here. It is f sub x, or let me say a partial z, partial x, dx, plus partial z, partial y, dy, which is really f sub x and f sub y. So when I substitute, I get the following. The partial derivative of z with respect to x is just 2x, so this is 2x dx, plus the partial derivative of z with respect to y is just minus 2, so this is minus 2 dy. So this is dz. Now I have to substitute at 1 and 2. X is 1, y is 2, but I need to find dx and dy. What is dx and what is dy? Dx, as always, it is just the change in x, the exact change in x. And for the x component, x changes from 1 to 0.9. So the change is 0.9 minus 1, and this is minus 0.1. dy is the change in y, delta y, and the y changes from 2 to 2.1. So the change will be 2.1 minus 2. 2.1 minus, and this is 0.1. Now I substitute here dz at the point 1 and 2 equals x is 1, so this is 2 times 1, dx is minus 0.1 minus 2, dy is 0.1. Compute, so this becomes just minus 0.2 minus 0.2, and this is minus 0.4. This gives us, so we have the following. So delta z, the exact change in z, is approximately equals differential at the point 1, 2, which is minus 0.4. So this is how to compute, how to estimate the change in z using differentials. So this is the approximation. In fact, if you compute the exact change, delta z, we notice the following. Delta z equals of terminal point, 0.9, 2.1, minus of 1, 2. When we compute, we get minus 0.39, minus 0, which is minus 0.39. This is the exact change in z. If we compare it with the approximate change, in fact, they are very, very, very close. So this is really a good estimation. Differentials gives us a good estimation. Let's now consider the following problem. The length and width of a rectangle are measured as 15 cm and 12 cm respectively, with an error of measurement of at most 0.1 cm and 0.2 cm respectively. Use differentials to estimate the maximum error in the calculated area of the rectangle. For such word problems, it is the first step is just to write the given information and then indicate what is required, okay, to find. Okay. So here we have a rectangle. So just let's draw a rectangle here. So it's rectangle. Okay. The length and the width of the rectangle. So I can take the length to be x, for example, here, and the width to be y. Okay. So we just give them names as variables, x and y. The length and width of a rectangle are measured as 15 and 12. So I have x equals 15. This is the given information, and y equals 12. Centimeter. Okay. With an error of measurement, always the error is just delta of at most 0.1 and 0.2 centimeter. So the error of measurement, which is delta x and delta y, at most, so in absolute value. Okay. With an error of measurement of at most 0.1 centimeter, this is corresponding to the length, so this is less than 0.1, and 0.2 for the width, less than 0.2. So the error is between -1 and 0.1, between -2, 0.2 and 0.2. So these are the given information. Now use differentials to estimate the maximum error in the calculated area of the rectangle. So the error in calculating the area. So really here we need to approximate delta the area, A for the area. So this is what is the question. Approximate delta area. And of course we approximate changes by using differentials as the question indicates. So really here we have delta A. The brief answer is delta A is approximately equals the differential. At the corresponding point when x equals 15 and y equals 12. When y equals 15 and 12. Okay, now we compute dA. But what is A here? The area of a rectangle, the area of the rectangle is just xy. The width times the length. This is the area. So now compute the differential of A, dA, equals A sub x dx plus A sub y dy. And this equals A sub x. When you differentiate A with respect to x, I get y. So this is y dx. A sub y, when we differentiate A with respect to y, we get x dy. Okay. Well, I know what is x and I know what is y. What remains is dx and dy. Well, we need to find the maximum error in the calculated area. So for that we take for dx the maximum possible error in the measurement, which is 0.1. This is the maximum possible error. Okay, 0.1. The same thing for dy. Since we want to calculate the maximum error possible in the calculated area, we take also the maximum possible error in measuring y. And this is 0.2. So delta dy is 0.2. So this is dx and this is dy. Now substitute. Now what is dA? The differential at the point xy equals 15 and 12. This equals, I have this formula here, y is 12 times dx, which is 0.1, plus x, which is 15, times dy, which is 0.2. Okay. Now just substitute this. So this is just evaluate. This is 1.2 plus 3, 33. This is a 3. 3. When we add, we get 4 point. We get 4 point. So delta A, the maximum possible error in the calculating the area, is approximately equals the differential, which is 4.2. This is the answer. That's it. Let's consider the following problem. The two legs of a right triangle are measured to be 6 cm and 8 cm respectively, with a possible error in measurement of at most 0.2 cm in each. Use differentials to estimate the maximum error in the calculated value of the hypotenuse. So first, we just try to write down the given information and then decide what is required from this problem. So we have the two legs of a right triangle. So we have here a right triangle. This is a right triangle. We have two legs. So let me call the first x and the second y. They are measured, the two legs of a right triangle are measured as 6 and 8. So I can take x to be 6 centimeter and y to be 8 centimeter, with a possible error in measurement of at most 0.2 centimeter in each. So the error in measuring x and measuring y, which is delta x and delta y, the maximum is 0.2. So this is h less than or equals 0.2, and this is less than or equals 0.2. So in both measurements, the maximum error is at most 0.2. Use differentials to estimate the maximum error in the calculated value of the hypotenuse. So this is the hypotenuse here, z. We need to approximate delta z. This is h, the equation. So these are the given information, and this is the equation. To approximate delta z, we use differentials as usual. So delta z is approximately equals dz at the given point, which is 6 and 8. So xy equals 6, 8. Well, we need to find dz and evaluate. But what is z? First, we have to find a formula for z. And using Pythagoras theorem here, we have the following formula. This is z squared, the hypotenuse, equals x squared plus y squared by Pythagoras theorem. We need z, so I can take the square root. So this is z equals square root of x squared plus y squared. Of course, we take only the positive square root because z is a length, so it is a positive value. So this is the equation for z. Now find the differential. Z dz. It is partial z, partial x dx plus partial z, partial y times dy. Find the derivative with respect to x. When you apply, you get h 1 over 2 square root of x squared plus y squared times 2x dx plus the derivative of z with respect to y. This is 1 over 2 root x squared plus y squared times 2y dy. I can simplify, just take the x's out. So this is just, let me write it as x over root x squared plus y squared dx plus y over x squared plus y squared under the root dy. So this is the formula for the differential of z. Now I need to evaluate at the point 6 and 8. So I know what is x and what is y. What is remaining is dx and dy. Well, we get dx and dy from delta x and delta y. Since we need the maximum error in the calculated value of the hypotenuse, the maximum possible error, we take for dx and dy the maximum possible error in delta x and delta y. So here, what is delta x, the maximum? Dx, we take it just the maximum possible value of delta x, which is 0.2. And here, we take dy to be the maximum possible value of the error, which is 0.2. So dx and dy are equal 0.2. Now you substitute. So this now the differential of z at x, y equals 6 and 8. Substitute here. We get the following. This is 6. This is 6. This is 6 over the root 6 squared, which is 36, plus 8 squared, which is 64. Dx is 0.2 plus y, which is 8 over the same square root 36 plus 64, and dy is 0.2. Here this equals the following. If I take 0.2 as a common factor, what remains is the following: 6 over, this is root 100, which is 10, plus 8, again over 10. So this becomes 0.2 times 14 over 10. 14 over 10. And this is just 2 over 10 times 14 over 10. And this is just 28 over 100. And this is 0.228. So the maximum error, delta z, is approximately equals 0.28. And this is the answer.